Hello again, and we'll be continuing the 2D convection equation using C++ object-oriented methods. And if you remember, last time we created a two-dimensional mesh, two-dimensional fields, and we passed the grid information to them, and we implemented a couple of functions to initialize a whole field to a single value and initialize a region of the field to a specific prescribed value, and we should continue from there, and we can also repeat this to v velocity as well, and so that we have both u and v with this initialized 2D region. Right, so now we need to define operators. Remember, we did them for the one-dimensional, so 1D overloaded operators. We can kind of copy paste this, except now this vector field will be a 2D, so just a lot of copy pasting here and there, and here, 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 and here. So now we got the entire thing in header declarations done. Right, it's time for us to write the 2D overloaded operator definitions. So let's give it a comment, say this is the 2D overloaded operators, and we can actually, I don't know if we should be copying these, but we can give it a go, copy, paste, and then change this to vector field 2D. Let's just first copy all this to 1D's change to 2D, so a lot of copy paste, but might save us some time in the end. So here, 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 and that's it. Didn't take much time. So here we can't initialize a two-dimensional vector field to single value, so we need to write vector field, vector of fields, and then say vec a 0 dot size copy. So until this bracket turns yellow, just keep writing brackets. Don't know what color it will be in your one, but here we can yeah, so we can do that here as well, here as well, here as well, but since this is b, we need to change these to vector b because only vector b is in the function definition. So here is okay because we got vector a as well. So let's see what we have defined. We defined two-dimensional plus operator, minus operator, multiplication using end-end, multiplication with a single value on left hand side and right hand side, and at the moment it's still not done because we need a second for loop. So let's do that and change this to j, 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 and change this to I size. Right, so we've done this a couple of times now, and here also put the j, so because it's 2D. Okay, so now we have everything that we need. We can copy this here, just change the sign to minus, change here, change the sign to multiplication, and Right, we have actually made a slight error, because if we initialize like this, then it will be initialized to the value of 0.0 everywhere. So I think I was wrong. I do apologize. Here should be vec A, here should be vec A, because the value here will be subtracted, sorry, vec B will be subtracted from this value. So here also should be vec A. Um, here is okay, right? Anyways, let's look at it again. So we got two vector fields in two dimensions, vec A and vec B. We initialize a new field called temp A with all the values of vec A and to the same size as well. And then we say that for every element, add the value at B. Okay, so that sounds good. And this also okay, minus this also okay, multiply. And here we need this for loop again. Here we got two returns, so delete one return. And here we need to copy this for loop and just say that it will be the double value multiplied by vec B. But we don't have vec A here, so let's just change everything to vec B. Okay, and copy this guy here. Alright, so that does it. We've defined all the operators for the two-dimensional fields. Before we do anything else, let's see if there's any errors. There is one error saying that there's no matching function to call this. Let's see if it is true. So vector of here should be size, right? So now we come here, also size should be okay. So here we don't take the size, we rather initialize everything to the same size as vec A. So this new temp vector will be initialized to the size of vec A, and also it will copy the values and member functions. But here we just need to create a temporary matrix of the same size but not the same values, and we multiply this vec B with this double value and say that this new vector will be the final outcome of this operation. Okay, so I hope you understand the difference. Here we need both vectors because we will be adding or subtracting B from A, and A is temp is a copy of A, so that's why we need to initialize to the same without saying that it will be an empty vector. But here we don't need that when we go to multiply with a double value. And similarly, if we define the divide operator or something like that, we could use this method. Okay, so let's build now and see what other errors we have to tackle. And luckily, I think everything is okay for this particular problem. So we have now defined the operators successfully for the two-dimensional fields. Let's call this 2D overloaded operators. Bear in mind that when you define overloaded operators, overloading can only be done for constant fields if you're taking two fields, and then return a new field which is not constant. So you cannot modify constant fields, constant vector fields. Okay, it just copy the values from them. That's why we need this constant to define this friend operator or overloaded operator. Right, so only one thing is left for us to do now in order to write the equations, which is defining these finite difference operations. So let's create a new namespace, and say this time we'll call it FD, finite difference. And here let's write a comment saying end namespace, because you might delete this bracket at some point when functions end namespace FD, end namespace FD1D, and let's build it. Right guys, so let's first go for the gradient, and it will be a vector field 2D again. So vector field 2D, and gradient also will take a vector field 2D, vector field gradient in x direction, and this will be initialized to vec.size and vector of fields vec0.size, and that should do it. And this will be also. So now we need another for loop because it's 2 dimensions, and then just change this guy to j, and change this guy to j as well, and the size will be vec i.size in the j direction. Okay, so let's delete this. And so one thing we could do is just do this gradient for all the internal points, keep the boundary constant. At the moment we don't have boundary conditions, so it doesn't really matter, but it's appropriate for us to define this for the internal field. So when I say internal field, I mean boundary nodes +1 in every direction and -1 in the end. So from 1 1 and -1 -1. So gradient will be simply temp ij dot value will be, because we are taking a backward spacing method for the gradients, it will be vec at I j dot value minus vec at I minus 1 j dot value, right, divided by vec at I j dot x minus vec. Remember, we passed the grid information, so makes life easy for us. So -1, and then we return it. So that's the gradient in x direction. Similarly, we could write for gradient y direction and say that it will be j minus 1 and j minus 1 be y, of course. So there we go. So we wrote now the two gradients in x and y. Okay, so let's build. So it worked fine without any errors. Let's look at our slides. What else do we need? Okay, so we got the gradients and we have defined the operators as well. So we are okay to go. But just for the sake of it, because in the future we'll be needing it, I am planning to implement the equation class. Couple of ways to do this. So the purpose of equation class is to write down separate equation for each vector or scalar field. To be honest, I'm not using scalar or vector fields separately here. I'm saying every two-dimensional vector field is a vector field. We could actually create separate classes for scalar fields, scalar quantities like pressure and stuff, but there's really no need to overcomplicate this at this level. So let's go ahead and say that there will be a new class called equation. And this class should include fields class. Right, so let's include this in our main file. So equations.h and build. It's good to build every now and then before you go ahead and do too much and then just confuse yourself. So fields.h is included now, and we want to basically say that the equation will take nothing but a constant fields vector field 2 dimension. Right, and therefore we should write constant fields vector field 2 dimension by reference and say final vec or something like that, and here also should be by reference. And let's initialize something called fields. So a member variable equation field. Okay, so let's call this equation field. You will come to understand this in a bit, so don't worry if you understand it right now. We are simply going to initialize this guy with final vec. So it will hold all the values that is in final vec will be copied to equation field. Okay, so can you create an equation now without this constructor? No, because the only valid constructor is a constructor that takes something in. We don't have a constructor like equations and this. No, we don't. So we need to pass a constant vector field 2D into this. Okay, so in order to do that, let's write our U convection equation. So equations, and we call this uconv equation. Right, so as soon as I open this bracket, note how it the suggestion appears that I should be using a vector field 2D. Okay, so here we can take under the namespace FD. So in this 1D finite operations, it will be returning to us a vector field 2D. So if you write FD and write grad x, it will return to us a vector field 2D. So can we call this in the constructor? Of course we can. So fd grad x of u, and let's see our solution algorithm is the gradient of u velocity in x direction multiplied by u velocity at I and j plus the v velocity multiplied by gradient in y direction. Okay, so let's see, we wrote the gradient of y direction as well. So simply it is plus fd grad y u velocity, but that's not enough, is it? Because we need to multiply this gradient with u velocity. So simply it will be u end, and here will be v end multiplication operated overloader. So we have kind of now defined this equation, everything inside the bracket, but at the same time we also need to multiply this by delta t and subtract it from u. Okay, so we will leave that for now and we will write the v equation as well. So v convection equation, and it will be grad x of v velocity, and let's see, yeah, so u multiplied by gradient of v velocity in x direction, v multiplied by gradient of v velocity in y direction. So we got that, we got this, and the v convection equation is also done. Let's see if it will build first. I forgot to delete this colon. Okay, so now it works fine. Let's write our for loop. So for int nt equals 0 to nt is less than solution 1d dot nt. I'm not going to change this because it's not a problem at the moment. nt plus plus, and let's copy everything here, but I doubt if I have the solution 1d created or not. So because when I changed to 2 dimensions, I deleted most of the stuff that was written for 1 dimensions. So let's create a solution object which will take these guys. So I'm just copying it here just to see what is needed. So int nt equal, let's say for now 4, double dt equal 0.001, double density equal 1.0, and double viscosity equal 1e minus 3, and we delete this, and then we call this solution 1d and sol 2d. We can name it anything. Let's call it sol and say it will be made up of nt, dt, density, and viscosity. Right, so now we can change this to the correct name, sol.nt. Let's build a project. Okay, so everything works fine, but at the moment we don't have a way to pass the old velocities, store the old velocities. So u new will be equal to u, and v new will be equal to v. And sorry, that's not correct. U will be equal to u new and v will be equal to v new. And now we have found a way to pass the methods or store the old velocities, and we need to write a function in the equation class which will bring us a vector field 1D, and we will call it solve. This solve will take a double which will be dt, and fields vector field 2D and old vec old. Right, so let's copy this guy and put it here and say equations and put curly brackets. Before we do anything else, let's delete these names in the header file. Okay, so what do we want to do here? So basically in this we said that this new will be old minus whatever is the outcome of this. Correct. So what we will do is take a for loop from somewhere, so from here maybe, and vec old size, and create a temp field, also temporary field, which we will return. So here will be a temporary field of vec old dot size and vector of fields vec old 0 dot size. Okay, so temp ij dot value will be simply equal to dt multiplied by, remember that we initialized a field which will hold the values of the final outcome of the equation. So we could simply say that this is our equation taken inside the constructor, and this is our equation v taken inside the constructor. So let's keep it a bit more clear. Okay, so what we need to do is dt multiplied by this guy here, so ij dot value, and also the old is, if I remember correctly, subtracted from this. So sorry, this part is subtracted from the old, and this will be our final return. So return temp now. Okay, so we have this particular function which says that whatever is called inside this constructor will be initialized, not initialized, copied to the member variable equation field, and we will multiply the equation field with some delta time and the old vector will be subtracted from the old vector. So spend some time to think about it. It's not complicated at all. It's just a way to call the solve class, and therefore uh, u new will be equal to u u convection equation dot solve, and dt will be solution dot dt, and old will be u, and we get this u new. And similarly for the v new will be v new, but it will be v convection equation, and this will be v. And I think that is it for this particular. Yeah, we've written the u convection equation, the main terms, and we have found a way to call the solve method using some explicit time, step size, and the old velocity, and it will return us the final velocity field in u and v. So let's actually run this in the next tutorial, where we will write the file writing class, and we will visualize the solution, and from there it wouldn't be hard now to code the other equations, because we have implemented the most of the important functions, which is the finite difference operations, grad x, grad y. As we go along, we will write other stuff as well. For example, gradient. This is just a linear gradient, but we need to write central difference gradients and uh, Laplace operation and Poisson operations. So we can move slowly by implementing bits and bits and just testing whether they work correctly. So that way you can build your confidence. All right, so thank you.